How do you anchor a concrete highway where the earth ends and the clouds begin? In the heart of Sichuan, China, a structure exists that geologists called technical suicide. The fog breaks, a single concrete pier plunges into the abyss, one of many holding a ribbon of asphalt in the sky. We are at 3,000 meters, an altitude equivalent to nearly 10 Eiffel Towers stacked one on top of the other. The constant howl of hurricane-force winds slams into the concrete, a force that seeks to rip the structure from the cliffside. This is more than an engineering challenge. It's a battle against the planet itself. This region sits on a tectonic battleground, a fault line capable of unleashing tremors of magnitude 8. The ground shakes, the air screams, yet the highway holds. To understand how humanity defeated these impossible forces, join us on this journey. Subscribe and you won't miss a single step. The question is not just about strength, but about grip. How does a foundation find purchase in a vertical void? A sheer rock face plunging into nothing. The visible piers are only half the story. The real solution is hidden from sight, a mechanism that counters the blind fury of nature with calculated, invisible force. The secret lies in its invisible anchors. While engineering can conquer altitude, it must bow before geology. The first Great Barrier was not up, but forward, a monolithic wall of granite dividing China north from south. The Qinling Mountains, 100 kilometers wide, unyielding, impossible to bypass. To maintain a straight, high-speed corridor for trains traveling at 250 kilometers per hour, going over or around was not an option. The gradients were too steep, the detours too long. The solution was radical: go straight through. The result is a subterranean artery where 90% of the entire route runs underground or on elevated viaducts. A journey made almost entirely blind. This required a new generation of smart tunnel boring machines. These colossal machines didn't just drill, they analyzed. While tungsten carbide cutters ground through extreme hardness granite, a network of integrated laser sensors scanned the surrounding rock mass in real time. They search for microfractures, for any shift in tectonic pressure. It's a continuous, automated geological survey happening meters ahead of the main drill head. What was once a treacherous, day-long drive across a mountain pass is now a passage of less than an hour. But the machine never sleeps. The system continues to monitor tectonic activity non-stop, transforming a brutal journey through a mountain's core into a serene flight through a secure digital corridor. If piercing the northern mountains was a horizontal challenge, the south presented a vertical nightmare. Here, the fractured tablelands of the Yunnan Guizhou Plateau simply end. A sheer geological step, an abrupt 2,000-meter drop into the Sichuan Basin. A conventional road down this cliff face would be a death sentence of switchbacks and overheated brakes. So, engineers proposed a solution that defies logic. They would not go around the mountain, they would not go over it, they would go inside it. A heavy convoy approaches a vertical wall of solid rock. It doesn't turn, it drives straight into a gaping portal. The low rumble of the engines is instantly swallowed, then amplified, echoing in a massive granite cylinder. A heavy truck makes a full circle entirely inside the mountain before emerging from a different hole hundreds of meters below. It's a giant architectural corkscrew carved through the heart of the massif. This is a spiral tunnel, a masterpiece of structural geometry. Some are even built as double helixes, with two interlocking spirals descending in tandem. The entire purpose is to solve a physics problem: how to safely dissipate the enormous potential energy of a 2,000-meter descent, an altitude drop equal to the floor of the Grand Canyon. Instead of fighting gravity with brakes, the spiral extends the path. It forces vehicles into a long, controlled fall. The mountain becomes a hollow, engineered drum for managing velocity. By unwinding the descent over kilometers of internal roadway, engineers can dictate the laws of motion. They lock the entire system to a single, critical parameter. The road's gradient is tamed, never allowed to exceed a gentle 3 to 4% slope. This is the geometry of survival, carved in stone, ensuring a convoy's safe passage. The mountain's power remains, but it is now governed by one unwavering number: a gradient held below 3%. Piercing the granite of the north and conquering the 2,000-meter chasms of the south were not isolated engineering feats. They were tactical strikes in a single, massive campaign to permanently shatter the geological prison of the Sichuan Basin. For millennia, this region's geography dictated its destiny. It was an island on land, a wealthy basin sealed off by mountains that touched the sky. Its ancient paths were not roads. They were terrifying tightropes of rotting wooden planks, nailed into sheer cliffs, suspended over a fatal drop. The journey to Sichuan was said to be harder than climbing to heaven. This was not poetry, it was physics. But the 21st century brought an ambition that defied geology itself. The ancient barriers were systematically dismantled, replaced by a modern circulatory system of steel and concrete. This transformation is a macroeconomic triumph, a grid that has ripped millions of people from historical isolation and integrated them into the world. The impossible climb has become a journey of mere hours. Having conquered the Qinling Mountains in the north and the Yunnan Guizhou Plateau in the south, engineers were about to face the ultimate monster, the roof of the world and its raging rivers, demanding the creation of unprecedented technological heroes. To defy gravity above the roaring rivers and forge a path where physics itself seemed to surrender, engineers summoned a technological hero, a steel monster named the SLJ 900/32. This is not merely a crane, it is a mobile viaduct factory, a 92-meter-long Goliath that redefines the very concept of bridge construction. It weighs 580 tons. The process it performs is a symphony of extreme engineering. The machine picks up a prefabricated concrete bridge segment, itself weighing hundreds of tons, and slowly transports it to the edge of the abyss. A deep, metallic groan echoes as the colossal machine extends, its forward supports reaching across the void to rest on the next concrete pier. There is no scaffolding, no army of workers suspended over the valley. Beneath its tracks, only a dizzying emptiness. Then, with the precision of a surgeon, it lowers the immense concrete section into place. Millimeter perfect. A project that once would have consumed decades of dangerous labor is completed in just 5 years. This is the new paradigm, an autonomous mega factory on wheels, doing the impossible over and over again. The segment locks into place. A new piece of solid road exists where only air was moments before. The machine then inches forward into the misty chasm, ready to conquer the next gap. Such monster machines are ideal for viaducts, but what about where there's no support even for them? Over the roaring Dadu Canyon? Here, the gorge is a deep wound in the earth, where building piers into the riverbed was impossible, a technical and ecological dead end. The challenge required engineers to suspend a highway over a void. The answer is the Xingkang Bridge, a masterpiece of suspension engineering. It features a main span of 100 meters, hanging more than 200 meters above the water. But its true genius is not the visible structure, it is what lies hidden. The steep canyon walls offered no space for the massive gravity anchors that typically secure a suspension bridge's cables. The solution had to come from inside the mountain itself. Engineers drilled directly into solid rock, pioneering a method called tunnel anchoring. They carved 2 tunnels, each 159 meters deep, straight into the mountainside. Imagine a 50-story skyscraper. Now drive it horizontally into stone. Inside these rock chambers, the main steel cables are locked in place. A pure power move. The mountain itself is holding the bridge with its own hands. This visually light structure seems to float, defying the brutal, invisible forces of the canyon. The result is a vital link that simply ignores the chasm below, proving that human calculation can conquer the raw power of nature. Having tamed individual chasms, engineers scaled the technology to create a mega system that defies the laws of height. The Yaxi Expressway, a 240-kilometer ribbon of asphalt that connects 2 cities by climbing straight into the sky. This is not a gradual incline. This is a relentless ascent. For every kilometer forward, the road climbs 7.5 meters, a constant engineered push against gravity. The highway is designed as a single breathing organism built to survive one of the most seismically active zones on the planet. Its backbone is the Labajin Viaduct, anchored by piers reaching 229 meters high. These are not simple concrete pillars, they are a hybrid structure. A skeleton of steel is encased in high-strength concrete, creating a column that can flex and oscillate during a seismic event. A slight, controlled sway, not a catastrophic fracture. You can feel the tremor move through it, a life-saving vibration. Further up, the Genhaisi Bridge snakes across the mountainside like a steel roller coaster. Here, the ground itself is unstable, unable to support conventional massive piers. The solution was a material revolution. Engineers used enormous steel tubes, hollow and relatively lightweight, and then pumped them full of self-compacting concrete. The result is a structure with significantly less mass but uncompromised strength. It floats where others would sink. The road continues its climb, punching through the cloud layer. Below, the valleys disappear into a sea of white fog, a world erased. Above, only the mountain peaks and the endless asphalt remain, suspended in the air. But this sky road is just one front in a colossal battle for the roof of the world, where geology itself resists human presence. This is Western Sichuan, the antechamber to the Tibetan Plateau, a region where the average altitude soars above 4,000 meters and the very ground is a hostile force. Here, engineers fight a war on multiple fronts, against permafrost, the perpetually frozen soil that heaves and settles with the seasons, against thin air that starves engines of power, and against geology itself. This is a seismic battleground. Structures must be designed to withstand earthquakes of magnitude 8 without collapse. A total rethink of construction. The question becomes fundamental. How do you anchor foundations where the ground freezes solid, thaws into mud, and can be violently displaced by the planet's tectonic fury? Concrete must be engineered to endure daily cycles of freezing and thawing, a process that can shatter lesser materials from within. Every slope is a potential landslide, every valley a seismic risk. This is an economic war as much as an engineering one. The price of victory is staggering. Each kilometer of highway built here costs 10 times more than on the open plains. These few hours of travel, gifted by the viaducts, are not just a mathematical value. They represent the border between the agony of total isolation and the economic explosion of an entire region. Before, a truck loaded with fresh produce would crawl along a treacherous mountain pass, rain lashing the windshield, wheels slipping near the edge of a cliff. Inside the sealed cargo hold, the clock wasn't just ticking, it was a countdown to ruin as the faint, sweet smell of decay began to poison the air. A journey from the farms of Sichuan to the markets of Chengdu was a 48-hour ordeal, an entire weekend of risk. Now, the same cargo glides over smooth concrete, suspended high above the valley floor. The only sound is the whistle of wind against the driver's window. The same journey takes less than 4 hours, from 2 days to half a work shift, a 12-fold compression of time. This is more than just convenience. It is a fundamental economic weapon. The cost of transporting life-saving medical supplies and essential construction materials has plummeted, connecting once-forgotten autonomous prefectures directly to the national grid. For millions of people, the cost of moving goods hasn't just been reduced, it has been shattered, falling by over 90%. But for this 4-hour logistics revolution not to be swept away by the first landslide, engineers had to completely rethink the rules with working with mountains. It raises an obvious question. Why build these colossally expensive bridges and tunnels instead of simply carving a road into the mountainside? The answer is geology and economics. The rock faces of Sichuan are not solid granite. They are a fractured, unstable mass, saturated with water, a geological time bomb. Cutting a traditional road into this surface creates a fundamental weakness, inviting constant, devastating landslides. The cost is astronomical. Clearing the debris from a single major collapse would be more expensive than constructing an entire high-technology bridge span from scratch. But the design goes beyond just preventing disaster. By elevating the highway on massive piers, the delicate ecosystem on the ground is left almost completely untouched. Ancient migration paths for native animals remain open. Even the construction process itself was engineered for minimal impact. Along the Yaxi Expressway, integrated water recycling systems captured industrial runoff, ensuring that construction sediment never polluted the region's pristine mountain rivers. Ultimately, maintaining a conventional road cut into these vertical cliffs would have been a permanent financial and ecological catastrophe. But taming Sichuan's mountains with expressways was only the beginning. China is now moving to the next stage, a project on a scale that makes even those skyways seem like a preliminary test. This is the Sichuan-Tibet Railway, an investment of 40 billion euros, a budget that rivals the entire gross domestic product of a small European nation. The final, most complex section will cut directly through the Yarlung-Sangpo Grand Canyon, the deepest on Earth. This requires boring tunnels over 30 kilometers long through a geologically active nightmare. Here, colossal boring machines grind through solid rock. But this is not cold, stable granite. The tectonic pressure is immense, the rock itself radiating heat upwards of 40 degrees Celsius. The air is thick, suffocating. A constant vibration runs through the ground as heated stone crumbles and threatens to overwhelm the cutting face. A single mechanical failure here could be catastrophic. When completed by the year 2030, this railway will redefine high-altitude logistics, but that future is still being forged in the dark. Deep beneath the Himalayas, the drills advance without pause, boring into the planet's most hostile valleys. To peer through the mass of these superheated rocks and colossal concrete supports, we employ advanced visualization technologies. This is how we make the invisible visible. The human eye sees a solid structure, a static marvel of engineering. But inside the steel and concrete, a hidden war is raging. Micro vibrations, undetectable to our senses, pulse through the beams. Colossal internal stresses test the limits of the material with every passing second. To comprehend these seemingly impossible challenges, we integrated documentary simulations generated by artificial intelligence. These recreations peel back the layers of engineering, allowing us to witness technical details that are otherwise lost. A world of physics in constant, violent motion. This entire journey was a testament to overcoming barriers once thought absolute. A story written in steel, high above the clouds and deep beneath the earth. A final thought remains. Of all these structures, which was the hardest to conquer?